Two right circular cones with vertices facing down as shown in the figure below contains the same amount of liquid. The radii of the tops of the liquid surfaces are 3 centimeters and 6 centimeters. Into each cone is dropped a spherical marble of radius 1 centimeter, which sinks to the bottom and is completely submerged without spilling any liquid. What is the ratio of the rise of the liquid level in the narrow cone to the rise of the liquid level in the wide cone? First, we want to focus on the volume, just what's the formula for the volume of a cone. So we'll write that over here. So the volume of a cone is going to be 1/3 pi r squared times h. So if we want to find the volume of the narrow cone, that's going to be 1/3 pi 3 squared h1, which comes out to 3 pi h1. And then for the volume of the wide cone, that's going to be 1/3 pi 6 squared h2, which comes out to 12 pi h2. So since the volumes are equal, we're told, then it's going to be true that 3 pi h1 is equal to 12 pi h2. Divide both sides by 3 pi and divide both sides by h2, and we get h1 over h2 is equal to 4. So we're going to come back to that. That's going to be helpful. And so for each of these cones, I'll draw the narrow cone right there, and then wide cone here. So they start out with their levels of liquid. But when the marble is dropped in, so there's the marble there, when the marble is dropped in, the water level is going to rise. So for the narrow cone, let's say it rises up to here. And that new height, since this cone, the vertex angle is the same, this cone with increased volume, the height is going to rise by the same proportion as the radius. So let's say this was h1 before. This is h1 times a, and then the radius of this is going to be, let's call it, well, the radius was normally 3, so it's going to be 3a. And same with the rise here. It's going to be a proportional increase in height. So this was normally h2. Now this is going to be, let's call it h2 times b. And then radius here is going to be 6b. And so now the volume of this narrow cone, we'll call it volume of narrow cone 2, is going to be equal to, if we apply the same formula, we're going to get 3 pi h1 times a cubed, and the volume of the wide cone, call it 2, is going to be 12 pi h2b to the third. And so what we're trying to find, again, is the ratio of the rise in the liquid level in the narrow cone to the rise of the liquid level in the wide cone. So the rise in liquid level of the narrow cone is going to be h1a minus h1. Rise in liquid level of the wide cone is going to be h2b minus h2. So the ratio we're looking for is h1a minus h1 over h2b minus h2. And so this is interesting because we can factor out h1 on the top here, and we get a minus h1 times a minus 1. Down here we get h2 times b minus 1. So if we can just figure out, we know what h1 over h2 is, if we can find out what's a minus 1 over b minus 1, we're good. So something to notice here is these volumes, volume of the narrow cone, volume of the wide cone, So the ball was dropped in, the volumes are increasing by the same amount. So it's going to be true that these volumes are still equal. So we can say 3 pi h1 a to the third is equal to 12 pi h2 b to the third. And then we already proved that, or we already know that 3 pi h1 is equal to 12 pi h2. So this is then going to reduce to a to the third is equal to b to the third. And then from that, if that's true, then it's got to be true that a is equal to b, because it's increasing by a and b are positive numbers. So a is equal to b. And then if a is equal to b, then it's got to be true that a minus 1 is equal to b minus 1. So these will both cancel, and this ratio is equal to h1 over h2. And we had previously found that h1 over h2 is equal to 4. So the ratio we're looking for is choice E, 4.